Today's topic is going to be clues about evolution. Clues about evolution. Basically, evidence for evolution. Why don't you just write fossils? Let's write down fossils. Fossils are clues for evolution. We can look at fossils and see changes in them over time to conclude that animals have changed over time. If I find a fossil deep in a rock of a saber-toothed cat, and then higher up in the rock I find another fossil of the same cat, but it has shorter teeth, and then I find a fossil closer to the surface of the same cat with no long teeth, they're all short, I could probably conclude that the cat over time lost those sabers, those big incisors. So I can look at fossils and see what's going on. Go ahead and write both of these down. Relative dating and carbon dating. So relative dating, what you're going to do to determine the age of a fossil, you're going to see where it is in the rock. If it's higher in the rock, it's younger. If it's deeper in the rock, it's older. So you can kind of tell what layer of the rock it's in will tell you about how old the fossil is. The second one is carbon dating. You measure the amount of carbon in something. Most living things, all living things, are made up of a large amount of carbon, okay? And as things decay, the amount of carbon goes away. So when you die, okay, if we measure your carbon, you would have 100% of the carbon you're supposed to have. And if we buried you and looked at you 5,000 years from now, a bunch of the carbon would be gone. It would have gone back into the soil. And we can determine how much is left on how old your skeleton would be. So carbon dating, they do this a lot with like petrified trees, old tree stumps and things. You can determine how old it is by how much carbon is left in it. Okay. Won't worry too much about that. You don't need to write anything, but fossil records have gaps. Our fossil record is incomplete. Not all organisms become fossils. Actually, the situation has to be almost perfect to make a fossil. If you got a raccoon dead in the ditch or on the road, it's probably not going to turn into a fossil. It's going to rot and decay. Things are going to eat it. Okay, it needs to have perfect situation. A lot of time, volcanoes, if something gets killed in a volcano, it'll get covered up with rock and ash, and it'll preserve it really well. So there are gaps in fossil records. I want you to write down direct evidence. I might have mentioned this yesterday, but go ahead and write this. The development of antibiotic resistance in bacteria supports evolution. Penicillin, 100 years ago when it was invented, killed bacteria. Some of those bacteria became resistant to penicillin, and they reproduced and made more bacteria that was resistant to penicillin. So then we had to change the penicillin so it would kill it. So it's a constant battle between us changing the penicillin and bacteria changing so that the penicillin doesn't kill it. So direct evidence like that. Another example of direct evidence would be the moth story that I told you yesterday. I want you to write this down. You can pause if you need to. Write this down. This is most of the writing the rest of the time. I would pause because I'm going to go on here. Embryology study of embryo development, homologous structures, vestigial structures, and DNA. So pause this and write those definitions down. I guarantee they're going to show up, so don't skip this. But pause. Embryology is showing how closely related things are based on their embryos. The embryo is the developing baby. Okay, so if you look here, you can see fish, salamander, tortoise, chicken, pig, cow, rabbit, human. Okay, this is early in their development. This is later on. This is right before they are hatched or born. And you'll notice some things. Okay, you'll notice, I noticed the tortoise and the chicken seem very similar. By the way, these little things are gills. Okay, all living things have gill slits at some point in their development, even us. Then as we develop, those go away, they get absorbed. Some of them keep it, like the fish, most do not. But if you look at the tortoise and the chicken, pretty similar there. Here, pretty similar, even when they're about to be born. One has a shell, one does not, but they're pretty similar. The pig and the cow, pretty similar. The rabbit, okay? All these mammals kind of look similar. The fish and the salamander. So just something to think about, something kind of cool, comparing the embryos. Homologous structures are how your body is laid out, okay? And you'll notice, like with the human, this is our arm, so our upper arm here just has the humerus, just has one bone. Then we have two bones, then we have a bunch of small bones in our wrist, and a bunch of small bones in our finger, okay? The cat is kind of similar to us, one big bone, two small ones, some wrist bones, some finger bones. Even the whale has the finger bones in there, even though it's a flipper, okay? So something kind of interesting there. The bat has almost like long fingers, even though it's a wing. So something to kind of look at, homologous structures. Vestigial structures are things that no longer work, that we no longer use. Yesterday I might have mentioned the tailbone, okay? Tail, we don't have tails, but we have this little fusion of vertebrae at the bottom of our back that thinks that maybe we would have had that at some point. Your appendix, okay? A lot of people get their appendix taken out. It is a small little organ about the size of your pinky finger that does nothing, okay? The thought is at one point when we ate more grasses, this is just a theory, ate more plant material, that it was helpful in breaking that down. Flightless birds have wings, but don't use them for flight. But at one point, they could have. And then another thing that I thought was cool is there is a cluster of bones in the back end of a whale that do nothing, but it's just there. Almost like at one point it had back flippers or feet, or maybe it lived on land. So these would be vestigial structures, things that no longer do anything, but they're still there. I read somewhere that the pinky toe is getting smaller and smaller as our generations go on, and it's touching the ground less, which makes me think maybe in a few hundred years or 1,000 years, our pinky toe might be gone, and you'll be a freak if you have a pinky toe. I don't know, but just something cool to kind of think of. And then, lastly, the comparing of DNA. You can compare the A's, T's, G's, and C's to see how closely related something is. If you lined up a human's DNA and a chimp's, we share about 96% of all DNA. And we are closer related than rats and mice, according to our DNA. Although, despite all of that, there's still like 40 million differences between our DNA and a chimp, so there's still a huge difference. But I just thought that was kind of interesting. That is it for the notes.